Thanks, Scott, and thanks everyone for coming today. So today I'm going to be talking to you about neotectonics, the study of active faulting and earthquakes. My research is primarily motivated by a desire to understand the tectonics of mountain building and to quantify seismic hazards. I'm going to begin with a broad introduction of tectonic geomorphology and paleoseismology, showing you some of the tools that I apply to this set of problems. I'm then going to take you on a world tour of 3 different mountain belts under different tectonic regimes and at different stages of orogenic processes. On this tour, I'll show you some of the questions I can answer with these tools, and I'll finish with a brief discussion of some overarching themes. So I'm going to start with first principles. What is an earthquake? An earthquake is the energy that is released when driving tectonic forces suddenly overcome the resisting frictional forces on a fault surface. That slip occurs as a finite displacement across a fault surface with some length and some width. The amount of energy released during an earthquake is a function of the fault slip and the area of the fault surface. If an earthquake is big enough, it can rupture a fault to the ground surface, creating a surface rupture or fault scarp, like these more famous historic examples. The size and shape of a fault scarp is directly related to the displacement and orientation of the fault. Typically, earthquakes must be at least about magnitude 6 to rupture the ground surface. With repeating earthquakes, fault scarps and displacements grow progressively larger and entire mountain ranges are uplifted. Single ruptures like those on the previous slide might make scarps that are a few meters tall, but this image shows a compound fault scarp that is over 50 meters high, the cumulative deformation resulting from many earthquakes. When I look at mountains, I see this growth. How many earthquakes does it take to thrust rocks from the seafloor to over 7 kilometers in altitude? How much time is represented by this deformation? How big is each earthquake that lifts up this mountain? So what do earthquakes tell us about the driving tectonic forces that cause them? Earthquakes are an integral part of the tectonic process. The effects on earthquakes on the landscape provide a record of the motions of plate tectonics. The basin in this photo has opened due to active tectonics. When did that process start? Is that process ongoing? Has this been a steady, gradual process, or has that rate changed through time? And while this research is motivated in part by a desire to understand questions like these on tectonics and mountain building processes, it is also largely motivated by the desire to predict earthquakes. Societies want to know where, when, how often, and how big earthquakes can be. But prediction is currently not possible. And because the period of human observation is short compared to most earthquake cycles, we have to rely on paleoseismology to answer these questions, project the past records of earthquakes into the future. Seismic hazard models are largely based on paleoseismology. We know where faults are from creating detailed fault maps. How often earthquakes occur depend largely on a fault's average slip rate and its paleoseismic history. Slip rates are simply the average rate of fault movement over some period of time and are easily calculated by dividing displacement measurements by the age of displaced features. To estimate possible magnitudes, you can measure geometric properties of a fault, such as the displacement, rupture length, thickness of the crust, and fault tip, and relate these back to the seismic moment. I start most projects with fault mapping. Each of the 3 main types of faults leaves a distinct geomorphic signature. In general, faults create disruptions that cut across the landscape. Common geomorphic characteristics of strike-slip faults include a linear fault trace, laterally deflected streams, aligned ridges and depressions, and uphill-facing fault scarps. Common geomorphic characteristics of dipping faults include more curving, bending fault traces compared to strike-slip faults, steep, abrupt range fronts separating basins from mountains, triangular-shaped facets along a range with deeply incised narrow canyons between them, and uplifted fan remnants that preserve evidence of recent earthquakes. Mapping and measuring faults requires high-resolution imagery and topographic data. I use satellite imagery and aerial imagery, LiDAR, and structure from motion models to produce this topographic data. LiDAR uses pulses taken from an airplane or a terrestrial scanner to measure distances and reconstruct topography. More recently, I've been developing applications for mobile LiDAR scanning using the scanners built into the newest iPhones and iPads. Producing similar results as LiDAR, structure from motion uses photogrammetric principles to reconstruct topography using overlapping photographs taken from different locations. I mostly use images from drones or satellites for these reconstructions. Recent technological advances in flight control and positioning have dramatically increased the coverage area we're able to collect with a drone. Here's a comparison between a high-resolution satellite image, LiDAR hillshade, and 10-meter hillshade. These subtle faults pop out much more in the LiDAR hillshade, but they're completely invisible in the lower resolution elevation. Using these different types of data, I can map faults and make measurements. I use the principles of tectonic geomorphology to differentiate landforms by relative age and show cross-cutting relationships. In this image, periodic earthquakes along this fault have uplifted the alluvial fans and mountain range in the background. These periodic earthquakes, combined with ongoing geomorphic processes, have produced multiple different ages of alluvial fans that are uplifted and preserved. These are simple observations, but together they reveal a story about the history of the landscape. To quantify these sorts of rates of deformation, I take these maps and measurements of displacements and use quaternary geochronology to measure the depositional age of the faulted feature. This is an easy way to place limits on the rates of faulting. In general, I use luminescence, cosmogenic nuclides, and radiocarbon ages of detritus. I'm going to start my tour with the tallest mountains in the world, the Himalaya. This is a GPS velocity map of India, Tibet, and China. If we look from India into Tibet, the vectors are parallel and decrease in the direction they are facing. This is a signal of compression. This map shows that the Himalayan frontal thrust at the base of the Himalaya accommodates about 15 millimeters per year of the compression between India and Eurasia. This compression is periodically released during earthquakes, like in 2015, the magnitude 7.8 Gorkha earthquake. This earthquake killed several thousand people, destroyed numerous buildings in Kathmandu and the surrounding areas, and heavily damaged several World Heritage Sites. But what happened during this earthquake? This satellite radar map shows that the peaks of the high Himalaya, like Mount Everest, actually decreased in elevation, while the Himalayan foothills went up. This is counter to our intuitive model of the earthquakes building the mountain. So was this a full fault rupture? Did it rupture the surface of the fault? It did not. So our reconnaissance work and these geophysical models show that the front of the fault remained locked and only a deeper portion of the fault ruptured during this earthquake. This cross-section shows that seismicity during this event was limited to only a part of the fault. As the whole fault did not rupture, strain remained stored in the up-dip part of the fault system. The lack of surface rupture in 2015 leads to these earthquakes, these questions. Do Himalayan earthquakes ever rupture the surface? Should we expect bigger earthquakes? If so, how big would these bigger earthquakes be? When was the last one? To answer these questions, we can go to the fault itself. By excavating a paleoseismic trench across the fault scarp, I can look for stratigraphic evidence of past surface ruptures. In this trench is a series of river sediments that have been folded and broken by a low-angle thrust fault. This is a fossilized earthquake. These folded and faulted sediments were originally horizontal and continuous. The earthquake broke these sediments and formed a fault scarp, not dissimilar to the photos I showed earlier. That fault scarp then eroded and sediments were deposited on the downthrust side of the fault. Radiocarbon dates from the faulted and post-earthquake sediments show that this earthquake happened, in this case, between 1146 and 1256 AD. The vertical separation of these river deposits is about 5.5 meters. that corresponds to about 11 meters of slip on the dipping fault plane. That's a completely massive earthquake that would produce that much displacement. Similar studies have been conducted at dozens of sites all along the Himalayan arc. Each of these numbers is a paleoseismic site. By synthesizing the results of these studies, we can start to understand when and how big the last great earthquakes were. The result of this analysis shows that the last great earthquakes to rupture the front occurred from around 1200 to 1400 AD. If we extrapolate the current convergence rate over the elapsed time since the last big earthquake, that about 600 to 800 years, we see that 9 to 12 meters of strain is accumulated. This is similar to the displacements that are observed in these trenches, or about 11 meters that we see in our trench. So we can say that sufficient strain has accumulated to produce a similar earthquake as in the past. Based on the displacement and 500 to 800 kilometer long fault length, this could be a devastating magnitude 8.5 or even larger earthquake. This is one of the densest populated parts of the world, and this is a truly extreme hazard for the billion people living close to the fault system. If this happens in our lifetime, it'll be one of the greatest disasters we ever witness. And so to answer the questions, yes, we expect that bigger earthquakes should rupture the surface here. The next stop on today's tour will go to the Tien Shan. The Tien Shan Mountains are also part of the Indo-Eurasian collision, but here we have high rates of deformation concentrated over 1,000 kilometers away from the main plate interface. Zooming into the Tien Shan, we see that approximately 20 millimeters per year of convergence is accommodated across this mountain range, from the Tarim Basin in the south to the Kazakh platform in the north. I'm going to focus on work from my last 2 summers in Kyrgyzstan. This active fault map shows that the Tien Shan is comprised of a complicated series of intermontane basins and ranges, folds and thrust faults, while some of the most active faults also include both right and left lateral strike slip faults. These faults have historically produced a number of destructive magnitude 7 and 8 earthquakes. Together, these faults accommodate the geodetic deformation from the last slide. But how is that deformation distributed and partitioned among these many faults? Are some of these faults more active than others? And then why do we have so many strike slip faults in a compressive origin? What role do these strike slip faults serve? This is a structural cross-section from the Kazakh platform on the left to the Tarim Basin on the right. And this gives a sense of the structural complexity of the Tien Shan. The Tien Shan have had a long history with multiple orogenic episodes extending back to the Paleozoic. They're comprised of several accreted terrains, and they're cut by steeply dipping faults with both north and south vergent thrust and reverse faults. This cross-section also shows that deformation has progressed from the central parts of the range towards the margins, with the most recently initiated deformation encroaching into the Tarim Basin to the south. This drone image shows a series of glacial outwash terraces that have been cut by a thrust fault in central Kyrgyzstan. As this river has incised down, it has left behind this set of terraces, forming a broad set of steps up from the modern river to the highest, oldest terrace. Periodic earthquakes have displaced these terraces, producing this fault scarp. I made this model using photographs taken from a drone. Here I'm showing that drone model in 3D, and I've increased the vertical separation so that the topography becomes more pronounced. Viewing data like these in true 3D really facilitates visualization and understanding of the geologic relationships, and models like this can even be explored in VR. A really great tool for both research and teaching. The fault scarp cuts through all of these different river terraces, but the height of that scarp varies in each surface. In the younger surface, that scarp is about 15 meters high, while in the oldest surface, that scarp is about 60 meters. This demonstrates that faulting has been ongoing as the river has in size, an example of progressive deformation, where offsets in older deposits are larger than those in younger deposits. Age dating of each of these terraces will allow us to determine if the rate of faulting has been steady through time or if it's been more episodic. Farther along the fault is a beautiful example of active folding. Note the van here for scale. The fans here come down from the mountain front and they warp upwards before they're sharply cut off by this fault. The drone data I collected here reveal details of the kinematics and processes of folding and allow me to test different models of fold development. The incredibly detailed imagery not only shows clear evidence of folding and thrusting, but also these smaller extensional faults in the crest of the hanging wall resulting from flexure during the folding process. This topographic profile clearly shows the folding in the ground surface. The flat, ramp, flat morphology of the fold suggests that it has a fault bend fold geometry at depth rather than a listric fault. Next, we'll move to the Chinese-Kyrgyz border, where the valley floor here is over 3.5 kilometers in altitude. Here, I'm investigating a left lateral strike slip fault. That fault has a very clear surface trace cutting like a knife across the landscape. All along this fault zone is evidence of left lateral deformation. Here's a deflected stream channel. When there's sufficient offsets, streams form a new channel and the old channel no longer has a source drainage area. These beheaded streams are textbook evidence of active strike slip. Also, all along this fault zone, we found evidence of a recent earthquake in the form of ground cracking and even some fresh fault scarps, but there's no historical record of an earthquake here. At this site, the fault forms a series of right-stepping echelon shears, holding the lowest elevation river terrace into a small anticline that the stream has subsequently incised through. We sampled this folded river terrace for luminescence, and we find that the earthquake has to have occurred following 370 years before present. Geomorphic mapping in the basin of this fault reveals a relatively simple story of landscape evolution. During the end of the Pleistocene Ice Age, runoff from melting glaciers in the mountains filled this lake basin with water. The lake built this high set of beach berms. These massive alluvial fans then graded to that high level of the lake. After the ice melted and the water amount in the basin decreased, the lake elevation has dropped. That's since caused an incision event. This incision event has left behind a really beautiful set of markers that we can use to measure the rates of faulting. So using this kind of correlative mapping, I can leverage a limited number of geochronologic samples to determine ages of the entire landscape and place limits on the timing of offsets and rates of faulting. So this is the beach berm from the high stand of the lake. And we have an age of about 11,000 years for the age, which is similar to the age of these alluvial fans, about 12,000 years. We see we have a minimum offset of about 40 meters left laterally in that 12 to 15,000. Here's an example showing some of the drone data. We have a really clear fault zone and a whole number of different displacements. So here we have a 15-meter offset, about 28, 23, 27, 38, and so on displacements. And in total, we have about 30 kilometers of data along this fault zone. So how old are these channels that are displaced? Well, we know from the relative mapping, we can place limits on the ages of the fans and plot the ages of the fans versus the displacements. Doing that on this chart, and then taking the slope, the slip rate. And so here it's about 2.5 millimeters per year, average slip rate over the age of the fall. This was just one example of the many strike-slip faults in the Tien Shan. Most of these faults have evidence of recent surface ruptures, and several have slip rates much higher than any of the thrust faults. So back to one of the original motivating questions, why are there so many strike-slip faults in a compressive origin? My hypothesis is that these faults are reactivated and rotated reverse faults. Originally, a low-angle thrust might form like in the Himalaya. With continued deformation, that fault steps out again, and the hanging wall of the fault where the old fault is rotated by folding from continuing displacement. This process continues until faults are eventually rotated to a vertical orientation. These inherited structures then are in an optimal orientation to fail as a strike-slip fault. We also can look at this from a mechanical perspective, and Coulomb failure analysis shows us that it's actually easier for vertical strike-slip faults to fail than for low-angle thrust faults. So in that context, it makes sense that there are so many youthful surface ruptures along strike-slip faults, given optimally oriented pre-existing structures. So perhaps some of these strike-slip faults form as reactivated reverse faults. We may be underestimating their significance in accommodating regional strain. The presence of unrecognized faults and unaccounted for deformation can have significant implications for regional seismic hazards. For the last part of this tour, I take you to the Walker Lane fault system in the Western United States. Before showing you the modern tectonics, it helps to provide a brief geologic history of the region. For much of the Paleozoic through the early Cenozoic, the margin of Western North America hosted a subduction zone. This compression produced a high plateau known as the Nevada Plano. By the mid-Cenozoic, the Farallon Plate was completely subducted beneath North America, and that margin transitioned to accommodate the transform motion between the Pacific Plate and the North American Plate. This major change in boundary conditions resulted in the collapse of the formerly high plateau with widespread volcanism and extension, forming a broad series of horst and grabens known as the Basin Range province of today. This brings us to today's tectonic setting. This is a strain rate map of the Western US. Warmer colors are higher strain, while cooler colors are lower strain. From this map, there are several areas of higher strain. The highest strain rates are throughout southern and coastal California along the San Andreas fault system. And there's a broad zone of low to moderate strain across the entire Basin Range province. And there's another area of high strain that roughly follows the California-Nevada border, known as the Walker Lane or Eastern California shear zone. From this map, we can see that the Pacific North America plate boundary is not a narrow zone along the San Andreas Fault, but rather a very broad zone of distributed deformation. This is a GPS velocity map of the same region as the last slide. If we look at a transect from central Utah towards California, we see that the vectors slowly get larger. This is a signal of extension. As we approach the California border and the Walker Lane, the arrows are northwest oriented and become longer. As we continue westward to the coast of California, the vectors grow much larger, and that's a signal of northwest-oriented dextral shear. The Pacific Plate is sliding northwestward past the North America Plate at a rate of about 50 millimeters per year. Most of this motion is accommodated by the San Andreas Fault system, but about 20% of that motion, or 8 to 10 millimeters per year, is accommodated by the Walker Lane system. There's a lot going on in this slide, so I'll try to take you through it. Fault orientation, this northwest-oriented dextral shear field, generally dictates the kinematics of each fault, following these basic principles from structural geology. Walker Lane is comprised of mostly northwest striking right lateral strike-slip faults and northeast striking left lateral strike-slip faults and north striking normal faults. If we look at GPS profiles across the Walker Lane from north to south, we can see that the total amount of shear going from north to south decreases from about 6 millimeters per year in the north to about 10 millimeters per year in the south. In the south, we can also look at the slip rates of faults in these different profiles and compare them to the GPS rates. In the south, there's good agreement. We have about 9 millimeters per year of the total 10 accounted for by geologic slip rates of faults. But in this region in the north, we have very few strike slip faults and we can't make up that difference. So we're missing slip. If the slip isn't along strike slip faults, how is that shear accommodated? Where is that missing slip? How are we accommodating shear through here without strike slip faults? To start, I looked closely at all of the faults across this region using mostly airborne LiDAR data and field investigations. Here I provide just one example of that analysis. The margin of Smith Valley, Nevada, is a prominent normal fault bounded range. This range has triangular facets and young normal fault scarps are found in the alluvial fans all along the base of the range. Yet nowhere looking carefully in the LiDAR data and in the field do I see evidence of lateral displacements. This hillshade, this is just to give an example of how we calculate a slip rate here. So this is a LiDAR hillshade showing the fault scarp, several different generations of alluvial fans. If we divide the height of the scarp by the age of those different alluvial fans, we can measure slip rates. And for this, we find two different, we can measure two different displacements by two different ages of these different alluvial fans that are cut. So, but with both different measurements, we get the same result of about 0.6 millimeters per year. This is quite slow. We'd only expect an earthquake every few thousand years. But here we see no evidence of lateral slip. Why is that? Well, if we think about it from a process perspective, any lateral offsets that might occur along this range will be in an obliquely slipping event might be quickly buried by the collapse of the fault scarp. The geomorphic rates of erosion and deposition might outpace the lateral tectonics. So it's possible that this range could be accommodating some oblique motion. And in fact, the orientation of the range and much of the geometry suggests that it might be, but any evidence of lateral shear is obscured. So if we don't see direct evidence of lateral slip on these faults, what should we expect during an earthquake? Fortunately, several recent earthquakes provide examples of how lateral slip might be accommodated in the Walker Lane. In July of 2019, in the southern Walker Lane, 2 strike slip earthquakes occurred on conjugate faults on subsequent days. Both of these faults were previously unrecognized. Their occurrence raises the question, do these faults always rupture together? To answer that question, I can study the rupture. We collected high-resolution UAV images covering much of both fault ruptures in the days following the earthquakes. Magnitude 7.1 rupture forms a clear surface trace with a raised mole track. This is a common feature in strike slip rupture. Right lateral fault forms a left stepping an echelon pattern. The fault here produced more than a meter of right lateral displacement, which you can see if you look at the margin of this road here offset. I excavated trenches across these ruptures. Here, the faulting has produced a small uphill facing scarp in this river channel. That little more than a year after the earthquake, sediments have already been trapped behind the damming produced by this scarp. This is a perfect environment to record long-term deformation. The trench revealed a sequence of lacustrine and beach sediments. This area was submerged at the end of the Pleistocene by a massive pluvial lake. Within those lacustrine sediments is a fault strand that is then buried by younger river sediments. This is evidence that an earthquake occurred after the deposition of the lacustrine sediments, but prior to the deposition of these overlying sediments. Then in those river sediments is another fault strand that is capped by even younger river sediments. This is evidence of a second, younger earthquake. All of these sediments are then cut by the 2019 rupture. Thus, there is evidence for 3 total ruptures since the deposition of these sediments. You are all the first to really see these results, but the dating results indicate that these ruptures occurred at about 8.6 thousand years and after 1.6 thousand years. Recurrence times then thus are 7,000 years between these 2 events, and then less than 1,600 years for the younger event. This result suggests that this fault has an irregular recurrence behavior. Next, let's look at the conjugate left lateral magnitude 6.4 rupture. In this image, you see a primary fault zone with more distributed faulting over a 50-meter wide region. Note the small left lateral offsets on these roads. While the right lateral magnitude 7.1 was left stepping, this left lateral rupture produced right stepping and echelon breaks. This is typical behavior for strike slip faults. Again, here we excavated a trench to understand the past history of this fault. At the bottom of this trench is a buried soil that we correlate to a regional climatic change that occurred at the Pleistocene-Holocene boundary. Here I only see deformation from the 2019 earthquake in the overlying sediments, suggesting that 2019 was the only rupture of this fault during the Holocene. In contrast, the 7.1 produced 3 earthquakes during the Holocene. So to answer the question, no, these 2 faults do not always rupture together. And not only does the magnitude 7.1 fault produce bigger earthquakes, it also produces them much more frequently. Now we can look at another earthquake that occurred in the Walker Land. The 2020 Monte Cristo Range earthquake occurred in a large right stepover between some of the major right lateral faults in the Walker Land. Here, left lateral faults allow for the intervening crustal blocks to rotate as this stepover transfers deformation. Like Ridgecrest, this earthquake also occurred on previously unrecognized faults. The earthquake produced a strike slip focal mechanism and mostly ruptured a sequence of left lateral faults. Again, in the days following this earthquake, I collected high-resolution UAV images of much of the surface ruptures. These images show some of the complexity of the rupture. The fault had an extremely complicated network of subfaults that ruptured. In some places, there were simple through-growing ruptures, but in many places, we found these broad fields of cracks across the desert floor. There's little geomorphic preservation potential for most of these minor cracks, and subsequent visits after only a few months showed that most of the evidence of this earthquake has already been erased from the landscape. Unlike Ridgecrest, where the rupture is mostly confined to a narrow zone, here the ruptures are extremely distributed. This complexity is apparent on the fault maps we publish. Maximum fault displacement occurred on a primary fault core, but deformation was widely distributed and sometimes with a width greater than 1 kilometer. This site shows the maximum displacement during this earthquake with merely about 20 centimeters of left lateral motion. I excavated a trench across this site to determine whether this fault had ruptured before. Please ignore this high contrast at the top of this image and instead pay attention to the change here between the darker gray and the lighter gray sediments. Cutting through all of these sediments is the fault and fissure from 2019. However, there's a whole series of other faults that are capped by the darker gray sediments that did not rupture in 2019. This shows that this is not a new fault and that this fault has produced ruptures before, yet its geomorphic signature in the landscape is very ephemeral, and I can't measure any sort of long-term rates from this. So going back to the questions about the Walker Land in this northern region, where is the missing slip I mentioned earlier? The final example comes in the form of this wax model. The wax is heated and the surface quickly cooled with water to represent the brittle lithosphere over a ductile asthenosphere. The model is then sheared and we see this pattern of triangular shaped basins opening via block rotations, but really without any strike slip faulting. So now I've given you three hypotheses to explain this missing slit: large-scale crustal block rotations, sedimentation obscuring low slip rate oblique faults, and then complex faults with distributed cryptic ruptures that don't leave a lasting imprint on the landscape. Together, these processes work to accommodate lateral shear, but without really the traditional model of what defines a fault. This poses a challenge for seismic hazard models that rely on known fault sources. You might be wondering what's with all these earthquakes in the Walker Lane. Is there something to that? Well, if we look back to 1872, we see that there have been actually over a dozen earthquakes in the Walker Lane that have ruptured following a somewhat linear belt. Each of these faults has an average recurrence rate ranging from thousands to tens of thousands of years. As shown, they don't always rupture together, but clearly there's some geophysical process controlling this clustering of ruptures. There are similar patterns in subduction zones like Alaska, Chile, or the Himalaya, and in other intraplate settings like the Tianshan or the Apennine. While this might seem intuitive, we don't fully understand why this occurs, and this is an area of ongoing research. A final observation that I want to point out is the scale independence of faulting. Many of the faults in the Walker Lane form an echelon stepping pattern at a regional scale. Our high resolution rupture images reveal these beautiful en echelon patterns of shearing at a single rupture scale. And analog clay box models of these evolution of strike slip faults also produce these en echelon patterns, but on a centimeter scale. We see these similar patterns at the meter scale and at the whole fault system scale. So I started with two motivations: to better understand plate tectonics and seismic hazards. I've shown a variety of different tectonic settings and how in each of these earthquakes shape the landscape and build mountains. Each of these fault systems I've shown provides a snapshot of a stage of tectonic evolution. Many of the patterns we observe are scale independent. In simple systems like the Himalaya, we produce more simple earthquakes, while distributed systems have more complex earthquake patterns that can pose challenges for predicting ruptures. The Himalaya are a relatively young origin. The Tien Shan have experienced multiple different orogenic episodes. In the Walker Lane, a previous origin is now subjected to transtensional shear. This tour shows us that the complexity of a fault system seems to be controlled in large part by the tectonic history of the crust in a region. This really reveals the important role of inherited structures, which can be difficult to model as their understanding requires the integration of many different types of data. And so I want to end this by thanking many collaborators on all these different projects. And I hope today that you have enjoyed this tiny window into the world of neotectonics. So thank you, and I think we can open it up to questions now.
Thanks, Ian, that was great. Yeah, so we have two questions in the chat, so we can jump straight over to those. So the first one from Michael Taylor is, what are the uncertainties on the offsets?
Sorry, let me kill the pointer here. Can you ask that one more time? Sorry.
So what are the uncertainties on the offsets is the first question from Michael.
Yes, so in the Tien Shan example, the uncertainties I haven't completely pinned down, but with the really high resolution data, we can limit it pretty well by looking at kind of the maximum possible distance that it could be offset and the minimum possible distance it could be offset, and then assuming some kind of a distribution across that range. So it really kind of depends on the size of the offset, what the uncertainty is, and the orientation of the features and the preservation of the features.
So I have a quick question just to follow on from that. So some of your DEM profiles, they look very smooth. So do you have to do any filtering of vegetation or smaller scale features to sort of remove any influence of those?
In the Tien Shan, you can see in this picture in the background, there's actually almost no vegetation. So they actually are really smooth. If it's in a more vegetated area, then yeah, that can be challenging. If you've got trees or farms or something like that, you have to smooth the bushes or trees out.
Great. So there's another question from Michael Taylor. So how is the back rotation of the low angle thrust in the Tianshan consistent with your folding model?
So that's asking about this one. So in these, let me just show you the fold again. So in this is actually a really new fault that has stepped out from the range that's off the camera to the north of this image. So we know that these faults with time kind of march out. And we can see that looking at the Himalaya as a kind of a really big scale. We know these faults march out with time and that the hanging wall is rotating. So I think that's the model I have in my head of how that.
Great. I hope that answers your question, Michael. We have another question from Tamara. Hi, Tamara. So Tamara says, fantastic talk, Ian. For the second ridge crest fault, is there anything in the geomorphology to suggest that faulting may not always localize on that particular structure? I.e., could recurrent earthquakes happen on another weakness / fault within a few kilometers?
Yeah, there's other faults that are parallel to that. I think they're independent faults though, at the scale that structure is. So I don't think that like within a single fault we expect it to, you know, take a different path each time in that way. I don't know if that answers your question.
Great. We have another one just coming from Mark Hempel. So great talk, Ian. In the Tien Shan example, do you incorporate the folding along the displacement to estimate M?
That is a good question, and I don't know how to do that yet. I haven't actually really worked that up yet, so probably yes, but I haven't done that yet.
Great. So no other questions at the moment. Please post your questions in the chat if you have some questions. I'll just check the Q&A. So we have some more questions in the Q&A, Ian.
Yep.
So the first one from Maria. So what is the contribution of earthquakes to mountain buildings, and how do you explain the decrease in elevation during the Gorka earthquake?
Yeah, so the decrease in elevation during the Gorka earthquake is because you actually just have like really broad scale folding occurring without it actually rupturing to the surface. At least in my head, I think there's probably people here, like, I don't know if they're listening in that could tell better, but I'm sure John Elliott might have a better answer. But I think the whole, in my head, I imagine that the entire block of the Himalaya moves up during the full fault rupture, as opposed to just this kind of little kink in the system, in the Gorka earthquake.
Great, thank you. So no more questions at the moment. Please post them in the chat if you have any questions. Do we have any questions from the audience over in Leeds, Chi? Hello.
Hello, are we on? Yes, we are.
Yes, I can hear you now.
Anybody?
You have two more questions in the queue.
So we've got another question that's come up in the Q&A from Sukaka. Sorry about the pronunciation. So have you tried your methodology in the tropical area and the triple junction of tectonics?
Hi, so yeah, so in the tropical areas, it's definitely a lot harder to use drones and things like that. But I mean, in Nepal is kind of borderline tropical where we were working. It's not Indonesia. But we're actually working on a triple junction in Azerbaijan right now, which I didn't have time today to talk about. But yeah, it's can get really complicated when you have all these different faults at different orientations intersecting. And I think you have really high rates of tectonic change when you're in a triple junction. So different faults are really changing their behavior every earthquake, even maybe.
Great. So Peter Stiles wants to know if he can contact you when he's had time to absorb the talk. Great talk. So I assume you could put your email address in the chat. I think that's available on the Oxford University webpage as well, Peter. We have another question from Michael Taylor. Thanks, Michael. So does the simple Himalayan case assume the thrust wedge does not deform?
Sorry, say that one more time.
So does the simple Himalayan case assume the thrust wedge does not deform?
I don't think so. I think yeah, I don't think so, because the thrust wedge definitely.
Okay, so no more questions at the moment. Any more questions over? So questions over from you, Chi? Oh, we've got another one come up. So from you, hi Ian, thanks for your great talk. I'm interested in the Walker Lane, and I'm curious why the earthquakes occurring in swarms are not unusual in this region, e.g. the 2008 Mogul earthquake sequence, the 2011 sequence, and the 2014 swarm, and some other ones as well. It might be best if you just have a look at that in the chat, Ian. So do you have any ideas about this?
So that's a good question. I think it's a combination of one, you have this really kind of immature in a way fault system where you have all of these really different kind of complicated faults that intersect each other at really kind of with complicated geometries. And so you don't have the ability to have big through-going ruptures in some areas. So you get a lot of strain accumulated without a structure that can necessarily deal with that. I think that's part of it, but I also think you have kind of probably high heat flow and other things and maybe weak crust in that region that drive these swarms. I really don't have a good answer for that.
Thanks. I hope that answers your question. Thank you for that. Okay, I can't see any more questions at the moment. Please post questions in the chat. So we've got until 5 o'clock, so we've got 10 more minutes if you want to ask Ian any questions.
Can I ask Ian a question?
Yes, go ahead, Chi.
About the rotating fault model that you suggested. And I wonder, like, how widely do we observe such, for example, the fault, any systematic correlation between fault depth and fault age, for example?
I really don't know.
Cool.
It's kind of a very spacey model, maybe.
John?
So thank you, Ian, for your talk there. In regard the sort of California examples and also what this might mean for your Tien Shan work, but starting with California, you were saying quite a few of those recent earthquakes really weren't on previously recognized faults, or certainly not faults that would be considered major. So where do we go with this sort of bits of information? This keeps happening. So you refer to half of this as the science and half of this is the practical side of seismic hazard. If it relies, as you were saying, that seismic hazard relies on paleoseismic trenching, if these faults haven't been trenched before, what in our gap of knowledge, how can we move forward with this?
Yeah, I think that's a really good point that you're making, and I've heard other people make the same point. So, you know, we seem to have an issue where earthquakes happen on faults that we don't know about, and that's pretty common, I think, the world around. And we probably shouldn't be recording this, but I would say, you know, we need to balance our kind of models that are built purely on paleoseismology and observations from that realm with kind of regional geodetic models. And I think we can't use either of these alone to answer all of the questions, but we can definitely get at things like maximum expected magnitude. We can't really get without paleoseismology, I'd argue. Whereas you know, geodesy can fill in the rate that we might be expecting from other for the region that maybe we just know we're missing somehow.
Thank you.
Does the maximum magnitude take like a sequence of trenches along the full stretch of the fault to confirm like it did rupture the whole rupture?
I think, I mean, at least from trenches is really the only way we can measure the displacement of old faults. And so even if we're not looking at the fault length, because that's interpretive, generally, I would argue, we can really look at the displacement that we see in a single earthquakes from trenching. And there's not other good ways to get at that. Short of, you know, geomorphic studies can do the same sometimes, but it's never, I don't think it's ever as good as in trenching.
does it apply to both strike slip and thrust faults?
Yeah, strike slip, normal, or thrust faults. With strike slip faults, you have to do 3D trenching to get at displacements.
If I could have another one, it's about in the sort of percentage of off-fault deformation and what you count as off-fault. You showed some examples there where you have the on echelon, you have the radial shears, there's a certain finite width, but then you also talk about examples where you're moving to the kilometre scale. What's your feeling for the balance of faults that we really need to open up our aperture, our idea of how far away from a trace we need to look? Are these the exception, or actually are they a decent percentage of the catalogue?
Yeah, so I think that's a really like regionally dependent and fault dependent question. And so I think the Monte Cristo example, I think is really pretty extreme. Whereas I think, if we're looking at a more plate boundary style strike slip fault, it's going to be much more narrow. And there's, I think, a lot of papers and discussion on that, on the kind of from the modeling perspective, people have tried to approach that. But from, a one size fits all answer, I think it's hard to do at a kind of global scale for that.
So do you feel it's the maturity of the zone, the total strain accommodated, the lithology, or do we need to throw all those parameters in and build up enough examples to try and test them?
I think it's not even maturity in a sense. I mean, it depends on what you mean with these terms, really, right? Because they have kind of, I think, flexible definitions. But yeah, I mean, I think you really have to kind of maybe even holistically look at each fault to do that.
Thank you.
Okay, we've got another question in the chat. So from Tianshan. So hello, Ian. Thank you for the great talk. In Himalayan earthquake events, did you explore any cycle of events? So how do you connect hinterland earthquakes and earthquakes coming up to the Himalayan frontal thrust?
Hi, so I really haven't done that. I know one issue with and I don't know that too many people have, but I know one issue with even looking at multiple seismic cycles in the Himalaya is that you have these ruptures that are so big that you can't even really dig a big enough trench to capture more than one event. So I know that's been an issue in many places, is getting even multiple event earthquake records.
Great. And a comment from Michael. Thanks, Michael, for all your inputs. So just a comment, the back rotation model can be field tested. You should see a back rotation of the folded hanging wall strata. So a comment from Michael then.
Yeah, I mean, I think when we're looking at active folds, we definitely see rotated strata and back rotations. In this image, even you can see this at the top of the fold. There's back rotation of the fan surface that would have been smooth coming across here.
Great. Okay, well, we're coming up to 5 o'clock now. I can't see any other open questions. Have you found another one, Chi?
Yeah, in the Q&A box. How are you including all the new information you have presented in seismic hazard maps?
So I don't. So what I try to do is collect information that then people who are building seismic hazard maps can use as parameters in their models. So I try to just make the information I produce available for other people to use, because I'm not a seismic hazard modeler.
Great. So any more questions? I can't see any more questions. So if you do have any questions to follow up with Ian, you can put his email in the chat, or you can find his email on the Oxford University website. So thanks, Ian, again for a great webinar, and thank you all for the discussions. So we've got one last minute question come in. So are we talking back rotation means back wall tilting in the hanging wall?
I think that's what he meant when he asked us there. So yes. All right. Thank you, guys.
Yep, I think we're done. Okay, so thanks again, Ian. So next month we'll have a volcanic themed webinar presented by Edna Duwele, and we'll communicate that over email once the details are confirmed. So yeah, we'll be in touch. Enjoy the rest of your day, and thank you again for joining us all. Goodbye.